All right, go and get your homework out if you would, please. I gave you a proof yesterday to complete, in addition to copying out some work. And so you had a triangle sort of like this, okay, or however you chose to draw it. We called it ABC. And I gave you the median AM. Now remember, a median class is a line in a triangle that goes from a to the midpoint of the opposite side. And so you were given triangle ABC with median AM. And then we did something interesting. We went ahead and extended the median a little way until it would meet a parallel line from C. A line from C that would run parallel to AB. So we had this median extended, and it would meet this extension, this parallel rather, at a point we could call P. So we said that AM extended to meet, you could be copying this, Brecken, a line from C at P, so that CP was parallel to AB. I think I drew it better yesterday on the board. This drawing is not very good, particularly when you consider what we had to prove. And what we had to prove don't look like it up here. I think my midpoint is a little bit off, but it's okay. We don't trust our eyes, even when you have a bad day drawing, right? So we are going to prove, or we're going to prove, what? Josh?
That triangle PCM is congruent to triangle ABM.
The triangle PCM is congruent to triangle ABM. All right, so the triangle formed by the extensions is congruent to the lower portion of the triangle cut off by the median. All right, we're going to get to that in just a moment. Before we do, giving Brecken a chance to get it copied down since he was out yesterday, let's go and review some things we talked about recently. Had some theorems that I refer to as location theorems, because these theorems talk about where a point has to be located. For instance, we said, class, that if you had a line, and of course, here are my two endpoints, right? And I picked a point, not here. This is not the same distance from the two endpoints, but maybe this point is equidistant from the endpoints of the line. We proved that every single point that's equidistant from the ends of a line, class, must lie in the perpendicular bisector of that line. If it's equidistant from the endpoints, it's in the perpendicular bisector. Conversely, we proved if a point is in the perpendicular bisector, class, it must be equidistant from the ends of the line. We also proved that if we had some angle, and of course this point here is much closer to the right side than it is to the left side, but right about here, maybe about there. This point looks like it's about the same distance from the sides. We proved that every single point that would be equidistant from the sides of an angle, class, must lie in the bisector of that angle, in that angle bisector. Conversely, we proved that if a point is in an angle bisector, class, it will be equidistant from the sides of the angle. And based on that, we proved several things in the last lesson or two. We proved, for instance, that if we were to draw the three perpendicular bisectors of the sides of any triangle, those three perpendicular bisectors have to all meet in the same point. Even some goofy-looking, obtuse triangle. If you were to draw one perpendicular bisector and another perpendicular bisector and another perpendicular bisector, they all have to meet at some point. Now, we have a special name for three lines in general. Anytime three lines meet at a point, that's kind of unique, right? Two lines cross, big deal. A third line crosses at the same point. It's not a transversal anymore. It's like, it's weird. What do we call in general any three lines that meet at the same point? Brandon? Oh, yeah, you were thinking of the next question. Abby? Concurrent lines. Class, what is that? Concurrent lines. And we began looking at different sets of concurrent lines. This is just one set of concurrent lines that you can form with any triangle. And it's the intersection of the three perpendicular bisectors. And Brandon, where do the three perpendicular bisectors meet? At a point called the circumcenter. And the cool thing about the circumcenter is this point, because it's in the perpendicular bisectors, has to be equidistant from the ends of the lines. Or, class, we call these ends of the lines the where the sides come together, class? These are called vertices, right?
Oh,
For
yeah.
each one, these are the endpoints of a line, endpoints of a line, endpoints of a line. But as far as the triangle goes, those are the vertices, right? So the circumcenter is the same distance to every vertex, which means, class, I could draw a circle around the triangle. We would say if I draw a circle around a polygon so that it hits every vertex out its way around, class, the circle is said to be circumscribed, drawn around, circumscribed. So if I did draw the circle, running out of room, right? But if I drew the circle, it would be a circumscribed circle. How would I describe the triangle then? The polygon that's inside, so its vertices all hit the circle. We'd say the polygon, class, is inscribed because it's drawn inside, okay? And so we said we have the circumcenter. That's formed by one set of concurrent lines. Those, class, perpendicular bisectors. The circumcenter is formed by the perpendicular bisectors. We said there's another set of lines we could draw in a triangle. There's actually two more we've talked about. What's another one of those sets of lines, Lana, that we talked about in our last lesson, that they would all intersect? Michael?
The incenter.
Well, that's not a group of lines. We're talking about, but there is a point called the incenter. So here's the question: what lines meet at the incenter then? Anyone? The angle bisectors. Okay, so another group of lines in any triangle. Let me switch to some yellow chalk here. Another group of lines that will always intersect at the same point, will always be concurrent, would be the angle bisectors. So you bisect those angles, they're all going to intersect at the exact same point. We do call it the incenter. Do you remember, going back to Michael, do you remember why we call this point the incenter?
Because you can draw a triangle or a circle within that and it'll be equidistant.
Yeah, because I could draw a little circle inside, correct? Now, since the circle could be drawn inside, we call it the incenter. And the reason this is true, that's a horrible angle bisector, is because if a point is on an angle bisector, class, it's equidistant from the sides of the angle. Well, in this case, this point would be equidistant from the sides of all three angles, so it's literally equidistant from all three sides, so it would just form perfectly a circle touching all three sides. So we call that the incenter. So class, we said the perpendicular bisectors meet at the circumcenter. The angle bisectors meet at the incenter. What was that third group of lines we talked about that would all meet at the same point? Going back to our last lesson. Noah? We had angle bisectors, we had perpendicular bisectors, and we had... Abby? The altitudes. The altitudes. We said, now in this case, this is kind of weird because the altitude actually comes out here. And this altitude comes here, and this altitude comes down here. And if then you extended them, they should all just about come to the same point. So it's kind of weird with an obtuse triangle, but a little easier if you drew it this way, right? You get altitude, altitude, altitude. They all meet at a point. Now, you can't draw any cool circle with this triangle necessarily, but what do we call this point where the three altitudes meet? Back to Noah? Remember that an altitude is a line that's straight up and down, like you want your teeth to be. Straight up and down, not wiggly or side to side or sticking out like a warthog. The orthocenter, very good. Okay, so the orthocenter, class, that's where the three altitudes intersect. Okay, so let's rewind. Three groups of lines. In a triangle, they'll all intersect at the same point. That is, they will be, class, what's that term? Concurrent. Three lines that all intersect at the same point, concurrent lines. And so the one group of lines are perpendicular bisectors. Class, those meet at the? Then we talked about angle bisectors. They meet at the? Incenter. And we talked about the altitudes. They meet at the? Orthocenter. Good. There's one more group of concurrent lines we're going to get to a little bit later on. For now, though, let's pause there in our review and let's take a look at your homework, which had absolutely nothing whatsoever to do with all these concurrent lines. So let's take a look at that homework, and obviously your first statement, class, is always the given, and your first reason is always just the one word, given, yeah. So we're actually going to pick it up with statement 2, just for sake of time because I'm lazy. So statement number 2, I did have a clang word here in my given. What's that clang word that you see, Adam?
Median.
Median. And I actually referenced it even as I was drawing it. I said we draw a median, and I had to review, well, what is a median?
Midpoint.
It's a line that goes from a vertex to a midpoint in a triangle. So because I said that AM is a median, that means that something must be a midpoint. What? M. So we should have stated that M is the midpoint of BC. Now this is an easy point by definition of median of a triangle, by the way. This is an easy step to skip because in your mind you're just thinking, oh, it's a midpoint. Well, we do need to specify that M is the midpoint. How many took the time to state that M was the midpoint? Excellent. How many went straight to the next statement and said that
M is the midpoint.
CM equals BM? How many went straight to BM equals CM? You said definition of a median. Why is CM equal to BM, class? Definition of a midpoint, but you can't use definition of a midpoint if you haven't said you have a midpoint. So should have started off with these thoughts here. All right, questions so far? Michael?
I said CM was equal to BM, and then I said the median bisects the opposite side.
We don't actually have a definition that states that. The definition says it goes to the midpoint, and then because of a midpoint, it divides into equal sides. So kind of the right idea. I guess if we wanted to go ahead and state that, informal statements, the median of a triangle bisects the opposite side, based on the definition of a midpoint. We could work through these steps. We're not going to see it often enough to go through that, though. So just a matter of, including those little details, like in a court case, would you state your name for the court? Right? Just those little details that kind of cement the court case here, so to speak. Any other questions, comments so far? I kind of have another clangy sort of thing here, kind of ish, Brecken. What's kind of clangy about our given?
Parallel.
In general, when I see parallel, class, I want to think equal angles. And now I got a whole bunch of angles. I got 2 angles here. I got 3 angles here. And I got a couple angles there. So I got a whole bunch of angles here. Which angles might we get equal to each other here? Since we are trying to prove congruent triangles after all, the more angles we have equal, the easier our proof will be.
5 and 3.
Yeah, we could certainly say that angle 5 equals angle 3. Now that actually has nothing to do with parallel lines, but why does angle 5 equal angle 3, Brecken? The vertical angles are equal. And I should have used the shorthand there, vert. Started writing vertical, and what am I doing? All right, so 5 and 3 are equal. We could have said that. Of course, your numbers very likely were different than mine, but you could have stated that. You didn't necessarily have to for the proof, though. What's something we could have stated, though, because we had parallels, Brecken?
1 and 3.
Well, 1 and 3 both have the same transversal, right? But are their respective lines parallel? No, in fact, they're expressly not parallel because they form a triangle as the line is extended out. So, no, 1 and 3 certainly not equal. Remember, these are my 2 parallel lines right here. Lana?
Would it be 7 and 2?
Well, 7 and 2 have 2 different transversals, right? So in order to be equal, they have to have the same transversal. So it can't be 7 and 2. Adam?
Would be. Oh no, we don't have that angle.
Would it be equal to what?
What?
I heard you say B. B would be equal to what?
I mean it that way, but could you say B equals like 7?
Yeah, B and 7 are equal. They both have the same transversal, and they're on opposite sides of the transversal, and they're both between the respective lines. So class, angle B and angle 7 are alternate interior angles. So we could say number 5 that angle B equals angle 7 because, Adam?
Alternate interior angles and
Yeah.
parallel.
Alternate interior angles are equal if you got parallel lines. Close enough, right? It conveys the idea. By the way, those aren't the only alternate interior angles we could get equal to each other, Josh. I should mark these.
2 equals angle C. Wait.
Angle C, the whole angle at C equals angle 2?
No. Just like,
remember, here's my parallels. And the angle, the line that makes 2 happen is this transversal. One in P? Like that? The only problem there, Josh, is they both have the same transversal, but they're on the same side. So they're not actually, they're not alternate interior. They're interior, but they're not alternate interior, and their lines do not appear to be parallel. They do use the same transversal, but not parallel lines. So not 1 in P. Michael?
2 in P.
2 in P. Here we go, because they're on opposite sides of the transversal, and they're both between the respective lines, and they share the same transversal. So we could also say that angle 2 equals angle P, because alternate interior angles are equal if you got parallel lines. And so just a lot of clay sort of stuff, some equal angles because of the parallel lines. Now, do I have enough to get the triangles congruent at this point? Dylan?
Yes.
What do I got?
Side.
I got side, angle, angle if I want it, or side, angle, angle if I want it, or angle, side, angle if I want it. So yeah, number 6, we could say that triangle PCM is indeed congruent to triangle ABM. And you could have either used angle, side, angle, or you could have said side, angle, angle. If you went with side, angle, angle, you wouldn't actually need the vertical angles, and you could do this in as little as 5 steps. Did anyone do it in 5 steps? How many did it in 6 steps?
I didn't have everything right.
Okay. Questions at all? Anyone say I did it differently than you showed, but I think I got it correct? All right. Any questions then? You say I didn't do it right, but I'm a little not sure how you did that. Shouldn't be. I mean, it should be pretty straightforward. But any questions?
Label them as numbers.
That's always a big help. Numbers help. Now notice I didn't number B and I didn't number P because there's only one angle at P and one angle at B, so I'm lazy. All right, good. Any other questions on this? All right. Well, let's go ahead and get back to our concurrent lines. And there's one final set of concurrent lines. Theorems corollaries section of your notebook. Theorems corollaries section of your notebook. Obviously, this is a updated recording, so don't recall for sure if you've already copied this down, Gavin, but if you have not yet copied Theorem 31, go ahead and pause the video and give yourself a moment to copy Theorem 31 into your textbook. That's on page 111. The rest of you already did. That was part of your homework last night as well, was to copy Theorem 31 and read that for us, if you would, Lana.
The medians of a triangle meet in a point which is 2/3 of the distance from each vertex to the midpoint of the opposite side.
Now, this is kind of an interesting theorem. Read it again for us, if you would. Brandon?
The medians of a triangle meet in a point which is 2/3 the distance from each vertex to the midpoint of the opposite side.
Yeah, so it's really, really interesting here. Now, the main thing you need to know, honestly, truly, is that the medians of a triangle all meet in a point. That's the main thing that you need to know. So a median, remember, we just showed it here a moment ago at the homework, vertex to midpoint. Let's see, midpoint here. We have vertex to midpoint. And then midpoint right about here. And vertex to midpoint. As they all meet at the same point, all these three medians. That's the main thing you need to know. The extra part is the fact that that point is 2/3 the distance from the vertex to the midpoint of the opposite side. And so the book kind of does this interesting thing here where they find the midpoint right here and draw a parallel to the base and kind of come over here and make a little parallelogram here from midpoint to midpoint. And they basically show that this length equals that length. and this length equals that length, so you've got 2 of the 3 parts. So it's 2/3 here, 1/3 here, 2/3 here, 1/3 here, 2/3 here, 1/3 here. The unique thing about this is it makes the mass perfectly balanced around this exact point. Have you ever heard of something called the center of gravity or the center of mass? It's basically the one point on an object where if you were to suspend the object from that point, it would just hang perfectly level. For instance, if we decided to string up Brecken, and so we tied a rope around Brecken's neck, and we hung him from a tree, he wouldn't hang level, he would hang like this from his head, right? I'm not advocating for this, obviously. We love Brecken, okay? We don't promote violence, okay? We love Brecken. But Brecken would clearly hang like this, and that's what they used to do to people back in the day, criminals and such, and then there were some poor uses of it as well. But if we were to string him up maybe around the middle somewhere, if we could get it just right, we could kind of balance Brecken and hang him level. There are some rides at amusement parks, right, where they kind of dangle you hanging horizontally while you ride the ride. Is it Superman the ride? Is the one that has you hanging? Okay. So for that, they've got the support system hooked up just right, where it should balance most people horizontally. Well, if you took a triangle and made it out of, say, cardstock or something, and you were to run a needle and thread through it, it would dangle perfectly or hang perfectly level from that point. This is the actual center then of the triangle. We've talked about a circumcenter. Well, that's the center of the circle that goes around. We talked about the incenter. Well, that's the center of a circle that goes around the inside. We talked about an orthocenter. That's not particularly beneficial. This point is the actual center. It is like the center. Oid refers to like or pertaining to. So it is pertaining to the center. We call this the centroid. So if you would, in parentheses, put that at the end of Theorem 31. So you've got your Theorem 31 written out there, copied out, the medians of a triangle meet the point, which is 2/3 the distance from each vertex to the midpoint of the opposite side. In parentheses after it, put the term centroid. That is the actual center of mass for a triangle. Now, how to prove they all meet at a point? Well, I'm glad you asked. Turn over to page 112 in your textbooks. Turn over to page 112 in your textbooks. We are not going to take time to do the proof because the proof is already in your book. It's 22 steps. Yeah, so we're not going to copy that down because we're lazy. All right, so we're just going to let it be there in the book. Now, admittedly, the biggest part of the proof was the whole 2/3, 1/3. Okay, that took a big part of that proof, admittedly. Really, truly, in about 7 or 8 steps, you could get all 3 lines intersecting, and you see the work there. But anyway, I digress. What you just need to know is centroid is where the 3 medians intersect. Okay, so the perpendicular bisectors meet at the circumcenter. The angle bisectors meet at the incenter. The altitudes meet at the orthocenter, and the medians meet at the centroid. Terms definitions section of your notebook, let's put that there as well. Terms definitions section of your notebook, let's go ahead and put that term in the terms definitions as well. The centroid is the intersection of the medians of a triangle. The intersection of the medians of a triangle. The intersection of the medians of a triangle is the centroid. All right, now let's think about something for just a moment. Let's suppose I had a perfect equilateral triangle. Let's suppose it's an equilateral triangle. We know that an equilateral triangle class is also equiangular. So an equilateral triangle would be a regular triangle. Well, we also know that each angle class is how big? 60 degrees. If I were to bisect this angle, each side would be how large? 30 degrees. But we also know this, if I were to bisect the angle, because it's equilateral, it's also isosceles, isn't it? And the bisector of the vertex angle of an isosceles triangle is perpendicular to the base, and it bisects the base. So this angle bisector is also a perpendicular bisector, is also a median. Since it bisects, it goes to the midpoint, and is also an altitude. Now you realize if you did that from this angle, this is also a perpendicular bisector, slash median, slash angle bisector, slash altitude. And this line is also angle bisector, perpendicular bisector, altitude, median. So this point where all three of them meet in an equilateral triangle is all four things at once. Because these lines are perpendicular bisectors, class, it's the circumcenter. Forgive the circle. Because this point is where the angle bisectors meet, class, it's the incenter. Because these lines are altitudes, this point is the orthocenter. And because these lines are medians, class, it's the centroid. It's all of them at once. Questions on that? All right, so just kind of a neat thing. It's true with the equilateral triangle, that they've got all those points at once. Turn over to page 114 in your books. Turn over to page 114 in your books, and I would suggest you dog-ear this page. That means fold the corner of the page over so that it's easy to find this page later on. Because this page and the next page, pages 114 and 115, give us a good overview of a lot of the stuff we've talked about over the course of this year. This is your I'm working on a proof and I'm kind of stuck on what to do page or set of pages. Let's look at some things. If we wanted to prove triangles are congruent, well, notice there's 4 different ways in bold there to prove triangles congruent. Class, say them with me in the order they're written here. Angle, side angle, side angle, angle, side angle, side, and side, side, side. I think we got that down pretty well. So we don't need to read over that. Point number 2. Any two right triangles are congruent, class, by either leg, leg, leg angle, hypotenuse leg, hypotenuse angle. This next one, any two angles are equal. All right, so this would entail a proof that says, prove these angles equal. Here's a list of 7 different ways you can prove angles are equal. Read just the first one for us, Michael, nice and loud for the camera.
If they are straight angles, right angles, or vertical angles.
That's a pretty obvious way. You're probably not going to have something that easy come up as the main thing you're proving in a proof, but it might come up along the way, right? How about number 2, Brandon, nice and loud?
If they are complements or supplements of the same angle or of equal angles.
Yeah, we've actually done that a few times. You get these 2 angles equal. Oh, these are complementary, so therefore they're equal as well. Or get these 2 angles equal, and okay, these are supplementary to those, so they're equal as well. Number 3, we've used this a whole bunch, Lana.
If they are corresponding angles of congruent triangles.
Yeah, in other words, class, number 3 could just be
CBCT.
CBCTE. Number 4, we've seen this a whole lot, Josh.
If they are angles opposite equal sides in the same triangle.
We've done that a bunch, haven't we? Number 5, Brecken.
If they are alternate interior or corresponding angles of parallel lines made by the same transversal.
Yeah, that's important, remember, and I kind of emphasized that as we went through the homework proof. Same transversal's got to cut them, but if they're cut by the same transversal and they're alternate interior or corresponding, or class, it doesn't say it here, but alternate exterior angles as well would work. Number 6 is a fun one. Dylan?
If they are angles whose sides are parallel or perpendicular, respectively.
Yeah, in other words, if the sides are parallel, right side to right side and left side to left side, the angles are equal. And if the sides are perpendicular, right side to right side and left side to left side, the angles are equal. Right? By the way, this has nothing to do with this, but if the sides are parallel, right side to left side to right side, the angles are supplementary. Or perpendicular, right side to left side to right side, supplementary. All right, and then number 7, kind of a vague thing here, Adam.
By the use of axioms?
Yeah, by the use of axioms. That would be one of those where you've got this angle, and you've got this angle, and maybe they're divided into pieces, and you say, well, I know this whole angle equals this whole angle. I know that this angle is equal to that angle, so the remaining pieces are going to end up being equal because, well, the whole equals the sum of its parts. We can substitute the parts in for the wholes. We can subtract away the parts that are equal. That's what it's talking about, use of axioms. Addition axiom, subtraction axiom, substitution axiom, whole equals sum of parts axiom, that kind of thing for number 3. And on a similar note, number 4, any two lines are equal, Noah. Number 1.
If they are corresponding sides of concurrent triangles.
Yeah, CPCTE. Number 2, Abby.
If they are sides opposite equal angles in the same triangle.
We've seen that a bunch. Number 3, we've used this a few times. Michael?
I have lost where we are.
We're on Roman numeral 4, number 3.
Okay. If they're opposite sides of a parallelogram.
Yeah, lines are equal if they're opposite sides of a parallelogram. And this is kind of interesting. Number 4, Brandon.
If they are segments between parallels which are equal segments from another transversal.
Yeah, that's that theorem 24. If you got equal segments on one transversal by these 3 or more parallels, well then these segments are going to be equal as well. And of course, number 5, use of axioms.